Lavender. Okay, good morning. Let's see, Lavender. Okay, yes. No. What's, Jones. Okay. Smith. Okay, can you all hear me okay?
Yeah.
Okay, good. Alrighty, we're going to a couple of things real quick. Before I have posted.
Dr. Zainab, can you let Kiara Humbert in?
Yeah, she's in now. I posted the review for the test and final exam. Test 5 for chapter 4 and 5.1 and 2 is posted. I'm going to post the homework quiz today, and that will be due not this coming Sunday, but the following Sunday. And the final exam is already, well, I have it done, but it'll be posted after you finish the last test. And the review for that is already on Blackboard, and you should have received a copy of the final exam review. Monday, we're going to go over the test 5 review. So you want to go over that sometime between now and Monday, so that if you have any questions, we can address them. Okay. So we've got this lesson 5.3 and one more lesson, and that'll be all the new lessons. And after that, after Friday, after tomorrow, we'll just be going over review for the test and review for the final. And also be sure to do the QEP essay quiz number 2. Cassidy, make sure I get you on the attendance before you leave. Let me go ahead and get it now. Sanders, got it. All right. So we're doing lesson 5.3, inverse functions, and we probably will have time to get into lesson 5.4. This lesson here is really short. Actually, the last 2 lessons are really short. So we may even finish early on Friday. Okay, so we're working with inverse functions, and you should have had that in previous courses. A lot of this is review, but there is one thing when we get into differentiation for inverse functions and in the end of the lesson. Okay, here we have verified that one function is the inverse function of another. Determine whether the function has an inverse function. So these 2 objectives should be pretty much review, really. And then the last one, find the derivative of an inverse function. That should be new for you. Okay. The definition of an inverse function we have g, that function g is an inverse function of function f, when if we can compose a composite function where f is composed with g, in other words, we insert g within f of x and everything cancels and all we get is x for each x in the domain of g. And then if we switch it, g composed with f of x, in other words, we put f of x in and everything cancels and all we get is g for each x in the domain of f. So in other words, if we have a function, let's say f of x is equal to x squared, and g of x is equal to the square root of x. If we write this as f, so if we basically, it's like we cut the x's out and put parentheses. So this would be parentheses squared. And then we're going to insert the g of x inside of that. So this would be the square root goes in where the square is. So this x is gone. All you have is just like a open parentheses. And then, so now x, the square root of x and square cancel and all you get left is x. So we can identify that as f and g are inverses of each other. Well, normally we would write this as this, it's not an exponent. This means the inverse of f. So now if we were to write this as g composed with f, so we cut the x out and cut the x out. So this would be square root. And now we put the g, we put the f of x inside. So for f of x, that was x squared. So again, the square and square root cancel and all we get left is x. So this is how we can check after we have composed a, after we have worked through and come up with our inverse function. This is a way to check to make sure that we did it correctly. We found the correct inverse function. Any questions with that so far? Okay, so let's continue on. And so that's what this is here. So we would say that function g is denoted by f inverse. It's not reciprocal. This is not reciprocal when you have the -1 with the f, not with a variable or a number, then that means the inverse. Okay. All right. So we're good there. So we recall that section P3 way back in the beginning of the course, that a function can be represented, and when we were in chapter P, represented by a set of ordered pairs, such as f of x equals to x plus 3. So if we put 1 in, you get 4 out, right? You put 2 in, you get 5 out. You put 3 in, you get 6 out, and 4 in, you get 7 out. So the domain is 1, 2, 3, 4, and the range is 4, 5, 6, 7. And this can be written as ordered pairs: 1, 4, 2, 5, 3, 6, and 4, 7 as our set of ordered pairs. All righty. So how do we find the inverse of a function? First thing we do is we substitute y in for f of x. Y and f of x mean the same thing. We can say y equals f of x. So we substitute f of x, we put y in its place. Switch x and y variables, solve for y. Replace y with the inverse function symbol, and then check using composite functions. F composed with its inverse of x, everything cancels and you get x. And then if you switched it, put the inverse composed with f of x, everything cancels and you get x. Okay, so that's always a good thing to do, is to check that. All righty, so here we have, so before we move on to this slide here, if we go back to this example, we have f of x equal to x plus 3. And we had the ordered pairs of our function as 1, 4, 2, 5, 3, 6, and 4, 7. Okay, so if we want to find the inverse to this set of ordered pairs, we would just merely switch x and y. So now this would be 4 is now x, 1 is now y for the inverse. We switch 5 and 2. We have 2 and 5, now it's 5 and 2 for the inverse. 3 and 6 is now 6 and 3 for the inverse. 4 and 7 is now 7 and 4 for the inverse function. Okay, so the domain for our original function was 1, 2, 3, 4. 1, 2, 3, and 4. And the range for the original function was 4, 5, 6, and 7. So now for the inverse function, the domain and range are switched. So now the domain is 4, 5, 6, and 7. Pick this up, 4, 5, 6, and 7. And the range is 1, 2, 3, and 4. So what was the domain in the function is now the range in the inverse, and what was the range in the function is now the domain. So the domain and range switched, just like the coordinates. All the coordinates switched. Well, the domain and range switches too. Well, that kind of makes sense. If you switch the coordinates, then they're gonna, domain and range is gonna switch as well. Okay, so let's take a look at, so in our steps, if we wanted to find the inverse to this function, okay, so I'm just rewriting this, f of x equals to x plus 3. We substitute f of x with y, so y equals to x plus 3. And then we switch x and y. So what is y is now x, and what is x is now y. And then we go ahead and solve for y. So we apply -3 to both sides, and we get x minus 3 equals to y. Okay, and then from there, we can apply the inverse function in for y. So that's x minus 3. So if we were to apply the composite f composed with its inverse function, well, since f of x was x plus 3, then it's like we're cutting that x out, put parentheses plus 3, and we're going to put the composite function in there, x minus 3. And so we get x minus 3 plus 3. The 3's go to 0, they cancel out, and all we get is x. And so everything, so it checks, and you can do it the other way too. Okay, well, we can also do this graphically as well. All right, questions with that? All right. Okay, so if we have, so let's take a look at these problems here. We want to match the graph of the function with the graph of its inverse function. Okay, so here we have an exponential graph. Okay, so I'm going to draw that on here. And actually, I'm going to start with the linear function first. So here we have, you look at the inverses, you pick 2 points. So this is 0, 6, and this is 1, 0, or 2. These are in 2 increments of 2. So this would be 2, 0, and this would be 0, 6. So let's graph that. And so this is 2, 4, 6, and this is 2, 4, 6 this way. So this is 2, and this is 6. So the graph is a linear function. Okay, and so this is our function f. So now the inverse, here's 6 and 2, 4, 6 again. Now, since this is 0, 6, then we switch the x and y coordinates, and now this is now 6, 0. And we take this x-intercept, x is 2, y is 0, and we flip those, and now it's 0, 2. And so we have our graph for our inverse function, okay? And whether, you can write it as f inverse or f of x inverse, same thing. A lot of times the graphs will just show like f. Okay, so that's how you do, that's how you find the inverse graphically. Well, in the inverse, the interesting thing about this is that if we were to apply this all on the same coordinate plane, where this is our inverse, then you get this where the 2 functions cross, they're also going to cross at the axes of symmetry. And so as the function moves away from the axis of symmetry, so will the inverse. As the function gets closer to the axes of symmetry, moving from left to right, so will the inverse. Okay. Now you're not going to have to draw it all on. You're just going to have to match the graph with its inverse, but that's how you would do it. All right, questions with that? All right, so the next one here, let's take a look at this exponential function. Okay, so here's our graph again, coordinate plane. And here's 2, and here's 2, and here's 4. Okay, and so this exponential function, if you look real closely, it starts, of course, it starts off at 0, and it goes up to 2, 4. X is 2, y is 4. So it comes up like this. All right, so you look for the point. They're not going to give you the point. You have to kind of look for it. So in this case, this would be like, here's 2 and 4. All right, and so you're going to, it's still going to start off at 0. So you still have that, it still starts at the origin. Now you switch it. And now this is 4, 2. 4, 2. And so it comes up and looks like that. Okay. So that's how you probably could look at the graphs and be able to pick them out. But if you can't, then you could always do this technique. All right. Okay. So again, so that's all we're going to do with that. All right. Questions. All righty. So the next thing we're going to look at is, oh, right here.
Photogenic.
Yes.
You put your PowerPoints online.
Yeah, I can. Basically, they're just right out of the book. But what I can, I'll do my best to see, because these are all just basically all I did was copy and paste right out of the book. So, but if I get a chance, I'll try to put the last 2 on there. Okay.
Okay.
All right. So here we have verify the inverse functions. Show that f and g are inverse functions analytically and graphically. So here we have, we're going to look at problem 13. Okay. So here we have f of x is the square root of x minus 4, and g of x is x squared plus 4. And notice they put a restriction on here. X is greater than 0. And so when we go look at this graphically, I'll show you why they put that extra restriction, x is greater than 0, in there. Okay, so let's take a look at these 2. Okay, so here's 13. And we have f of x is equal to the square root of x minus 4, and g of x is equal to x squared plus 4, where x is greater than or equal to 0. Well, why did they put this restriction on here? Because with a quadratic, right, it doesn't pass the horizontal line test. So if we restrict it to where it's just positive numbers, now it does pass the horizontal line test. Okay, so that's why so now it is 1-to-1. So that's why they did that. Okay, so basically we want to apply this f composed with g of x and see if we get x. If we do get x, then they are inverses of, and then we can apply it the other way, then they are in fact inverses of each other. So we look at this and we say, all right, we're going to cut the x out and put parentheses there. So this is f, cut the x out, put parentheses, equals to the square root. Where the x is, we cut that out, put parentheses, minus 4. Okay, and then we're going to put g of x in there. So that's f composed with g. And where this, and the other side of g of x, this x squared plus 4 is going to go where the old x was for f. So this will be x squared plus 4. Okay, questions there. So this will be, we can get rid of the parentheses. That's x squared plus 4 minus 4. The 4's cancel out, they go to 0. And we get the square root of x squared. Square and square root, they cancel out. And all we have is x. And we can say yes. f and g is inverses of each other. And let's try it the other way. So now we're saying we're going to cut, we're saying G composed with F. Okay, so we want to see if we get X there. So this will be G, and then where the X was, we cut it out, put parentheses, and then where the X squared is, we cut it out, put parentheses squared plus 4. And so now we're going to take the f of x and we're going to put that in. So this will be G composed with f of x, and where the x was, we put parentheses squared, we're going to put the square root minus 4 in there. Square root x minus 4 in there. And so the square and the square and the square root cancel out, they're inverses, and we get x minus 4 plus 4. The 4s cancel out, they go to 0, and all we have left is x, and we can say yes. F composed with G, we get x, and G composed with f of x, we get x. And so, yes, we can say yes, they are inverses. F and G are inverses of each other. Okay, so let's see what that looks like on the graphing calculator. So come back up here, and we're going to put in here, clear that, and I'm going to go make sure, check my mode. Let's see, I just want to make sure I'm in function and not on sequence. So we're going to put in here the first one, the square root of x minus 4. Okay, and then hit the down arrow for the second function for g of x, and that'll be x squared plus 4. And so we're going to go to zoom, and we're going to go to zoom. I like to go to zoom standard 6, Z standard. So we just hit 6 on here, and there's our square root of x. That's x1. Now remember, we restricted g of x to where x is just greater than or equal to 0. So it's only the right side. So here, here's that axis of symmetry I was talking about, where x is 1, y is 1, x is 2, y is 2, and so on, for y equals x. And so as the f of x moves away from this axis of symmetry, the g of x is also going to move in the same manner away from that axis of symmetry. So that's we verified it graphically. Questions there? All right. Okay. So that's that slide. Okay, so that's those problems. Okay, so the next one, the existence of an inverse function. Not every function has an inverse function, and theorem 5.6 suggests the horizontal line test for that. So as though if you pass a horizontal line through there, it should only go through one point. And so this would not be 1-to-1. It would not pass the horizontal line test. So that a function is strictly monotonic. Okay, so we're going to have to switch to the other period here in a second. So basically, when a function is monotonic, when it either is increasing through the entire domain, or increasing or decreasing through the entire domain. Here it's increasing, reaches a pinnacle, and then it's decreasing. So this is not monotonic. So we'll get the steps of existence of an inverse function is if and only if it is 1-to-1. So it would have to pass the horizontal line test in order for it to be 1-to-1 or monotonic. Okay, so we'll come back with this. Let's exit out and come back in a moment. I'll see you in a few seconds.